Yeah, firstly, with the expression my thanks to the organizer of ICCF26 to present our result here. Most of people know I was doing calorimetry on palladium heavy water calorimetry these years. And now today's topic is some little bit difference. We studied the palladium nickel and palladium nickel zirconium zirconium alloys in hydrogen gas, in deuterium gas. This is a collaboration of the work. I mostly responsible for calorimetry. Our work is inspired by the Japanese scholars. First is Professor Arata and Zhang. They are observed excess heat in palladium zirconia powders in more than 20 years ago. Another is Takahashi and Kitamura and other co-workers. They worked on palladium nickel zirconia powders and found excess heat more than 10 watts in about 2 months times. They made the sample using the multi-spinning method. And now we also use palladium nickel powders on the palladium nickel zirconia powders. We use different manufacturer method. We use ball milling. This is the initial palladium powders. We can see the average size of the particle is around 300 nanometers, and this is a picture of SEM of the palladium. And it is initial nickel and initial zirconia powders. The grain size is about 50 micrometer. We use high energy ball milling method. This is the micro mill, and this is the parameters during the ball millings. Firstly, we report the palladium 1 nickel 7 powder. And this is the left picture is our particle size of palladium nickel samples after different ball milling times from 0 to 10 hours, 20 hours, 30 hours, and up to 60 hours. We can find the average grain size from firstly is 20 micrometers and extremely is around 4 micrometers. And the figure B is the XRD patterns from after different times. We can find after 60 hours, there is only palladium nickel alloys. This is the SEM of the PN samples after different times. A is 10 hours, B is 20 hours, C is 30 hours, D is 40 hours, E is 50 hours, and F is 60 hours. We can find after 60 hours ball milling, the grain size is from 0.37 micrometer to 4.63 micrometer. This is the PNZ samples. And this A and B is SEM pictures, and C is XRD pattern. We can find there is a zirconia, the palladium oxide, and the palladium zirconium alloy, nickel zirconium alloys. And the green size is also decrease with time because the zirconia is harder, then the decrease is more rapidly than the PN samples. And this is a different picture of different composition of the zirconia. The first row is the PD1 9 nickel 7, and the second row is PD1 nickel 7 and zirconia 1, and the last row is for zirconia 14. We can find the green size is decreases with the increase of the zirconia. And this is the particle size from the for PN samples from 3,400 nanometer to only about 30 or 50 nanometers for zirconia for PNZ samples. And this is the hydrogen absorption curve for PN left and the PNZ right. Of course, we work only under low temperature. We can find with the increase of the ball milling time, the absorption capacity is increased. And this is a hydrogen absorption at different temperature. The black one is 400 centimeter, and the red one is the black one is 200 certain center C, and the red one is the 400 C, and the left is PN and the right is PNZ. We can find with the increase of temperature, the loading ratio decrease. All the result indicate the hydrogen absorption is mainly for PD. All there is a PD nickel or palladium nickel, the zirconium. Actually, only the palladium absorbs the hydrogen. This is the calculated result of the loading ratio or H2PD, and this result is consistent with the per palladium metals. And now is another result. Takahashi has found a sample after calcination will give more excess heat, and the second calcination is most active for excess heat production. So we purpose to do the simulate the calcination process. We oxide the sample under 100 degree for 12 hours. And this process, this is a simulated process of calcination. The first row is the SEM of the sample, and B is the nickel element, and C is the palladium element, and the second row is the oxided sample. E is the nickel element, F is the palladium element, and the G is the oxygen element. We can find after oxidation, the nickel and the oxygen is distributed evenly. However, the palladium is concentrated in smaller particles. Another is the oxidation of P and Z sample. The A, B, C, D, respectively, is the original heated in vacuum, oxidized in air, and deuterated after. We can find after heated, the grain size become larger. After oxidated, it also the grain size growing larger. But after deuterated treatment, the grain size becomes smaller. Then is the most important result, calorimetry of sample. Yeah, the left corner is the calorimetry calorimeter or CBEC calorimeter. We have 3 CBEC calorimeter of this type. And the mission room of the calorimeter is 36 centimeter by 31 centimeter by 32 centimeter. This is the calibration result. We can find we have calibrated it to 500 watt and give the uncertainty is only 0.12 watt or 0.024%. This is a schematic of the experiment apparatus. And this is A, and is also the calorimeter. And B is the inside of calorimeter. We can see the reactor here, and the inner wall is copper. And the that picture, C, the samples in the holder. Now this example of the excess heat. The left one is one example of no excess heat. We can find when we applied 200 watts, the measured excess heat is only 0.1 plus and minus 0.56 watt. 3 days later, we did the experiment again. Yeah, this time is there is excess heat. Applied power is also 200 watt, and the excess power is 8.92 plus and minus 0.78 watts. This is for the PN sample about 5 grams. There's another evidence of excess heat. We use 2 thermal couples. One is beside the holder, another is above the holder. The y-axis is a difference between thermocouple 1 and thermocouple 2. We can find if there is no excess heat, the difference is a negative value. If there is excess heat, the difference is a positive value. It means if there is excess heat, the temperature T1 is hotter than temperature T2. It means there is a heat source in the holder. Yes, this is another evidence of excess heat. Another most important result is the effect of oxidation. Yeah, this is 6 runs of experiment. First time we use hydrogen gas, the black curve. We can find there is no prominent excess heat. Second time with deuterium, the red curves, we can find there is no excess heat. Third time we is the blue curve. We can find there is prominent excess heat. It is 8 watts. This is the oxidation pre-treatment sample. And then we use helium. The green curve, the short green curve here, is for a short time. There is also excess heat. It means excess heat did not disappear using the helium gas. Then we use the deuterium gas again. We can find the excess heat is existed for 1 week. 1 month later, we use do experiment again. This time the excess heat disappears. This is another experiment for PNZ samples. The left pictures we can find the black curve is for the first time, the red curve second time. We can find only third time using the deuterium there is some more excess heat. If we replace the sample with the oxidation pretreatment, there the excess heat appears. The black curve is the first time, red curve is the second time, and the blue curve is the third time. This behavior is similar to our experience in palladium in heavy water. First is the pretreatment is important. Secondly, is the active of the sample is not always. First time might be not work, but the second time is give the best result. Of course, sometimes is the third time. But after repeated runs, the activation will disappear. Another result is the magnitude of excess heat depends slightly on temperature. There's the figure we can find. If we lower the input power and then we lower the input lower the temperature, however, the
3 minutes you left.
Okay. The excess power do not change, but if we the input power decrease greatly, the excess power also decrease. Here is another two examples. Other two examples. The first one, there is no excess heat. When we lower the input power, there excess power appears. But we change the excess power, input power, again, the excess power seems to disappear. In the second run, we increase the input power. However, the excess heat do not, there is no excess power. But after some time, after 2 days, the excess power occurs. This is another effect. When we using the inert gases replacing the working gas, yes, is deuterium. Yeah, there the excess power exists again. It do not disappear. Of course, this first time they only last about half a day. Secondly, we purpose to do the experiment, and we can find for the first time the black ones there is excess power, and then we using the nitrogen gas to replace the deuterium. There is also excess power. Of course, after 2 days it decrease. This result is similar to the LEC behavior. This is a summary of our samples for PN and PN. They are also worked in temperature of 300 to 500 degrees. Pressure is 200 and 2000 pascals. Reproduce it is 50% to 57%. The maximum excess power is about 9 watt and 1.3 watt, and excess power density is 1.8 kilowatt per kilogram or 0.18 kilogram. This is a conclusion. Firstly, is the palladium, nickel, and palladium nickel zirconia powders were prepared using high energy ball milling, and oxidation pretreatment is key for excess heat production. The third is temperature change might stimulate excess heat, and four is replacing deuterium with inert gases did not affect excess heat in short time. And the five is excess heat over the 1.8 kilowatts per kilowatt with reproducibility of 50% for PN sample, and 0.18 kilowatts per kilogram with reproducibility of 57% for PNZ samples or wetted. This is all our report. Thank you.
Thank you very much. Any questions or comments?
Thank you. Could you describe what high energy ball milling is, please?
You want me? Yeah. What do you want to know about the high energy ball milling? Pardon?
Is it cryo? Is it cold? It looks like it's not cryo.
Sorry.
Is this a normal ball milling setup? Or why do you call it?
Yeah, I think so. This is the powders is using the chromatograph ethylene. They are using the liquid. Of course, it is cool milling and not in air. We using grinding balls of the tungsten carbonate about 1 millimeters diameters, and the rotation speed is 500 revolution per minute. Ball to material ratio is about 10 to 1. Of course, another parameters also used. I did not report it in details here.
Okay. Any other questions or comments? Okay. Then thank you very much, Mr. Zhang.